Okay, so just let me share the screen. Okay, so yeah, welcome to the live session for the course Fundamental of Fluid Mechanics for Chemical and Biomedical Engineers. This is the live session for week 10, and today's topic would be extensively covered on boundary layer. So this week was so the week 10 extensively discusses about the boundary layer. So yeah, and external flows in general, or flow over a flat plate. So yeah, okay, so yeah, boundary layer. So the theory of boundary layer was introduced by the Ludwig Prandtl. So, and why did he introduce that? Because in the previous week, as you might have gone through that, okay, in viscid flow, they generally do not show when you analyze or when you just do the analytical solution of the flows. And when you assume that the flow is inviscid, you will never see the drag and lift coming into play. So for that particular reason, the concept of boundary layer was introduced. So now with the introduction of the boundary layer, so what actually is the boundary layer? So let me just start with the boundary layer thickness. I'm denoting, or generally it is denoted with the Greek letter delta. So mathematically, the boundary layer can be defined as mathematically the boundary layer thickness can be defined as that y is equal to delta, u is equal to u infinity free stream velocity or bulk velocity. Okay, so if, if this is my solid flat plate and, and this is my u infinity free stream velocity, then the boundary layer will start from its inception, it will be from the start of the plate. It will go, and then there will be a sharp increase. That is the turbulent boundary layer. So this thickness delta, which is a function of x and y. So this is the your boundary layer thickness. Now this can be divided into two sections. So if you divide it, basically laminar boundary layer or terminal boundary. Sorry, yeah, turbulent boundary layer. Sorry. So what you can do is So obviously in between the laminar turbulent boundary, so it is not a very, uh, not a very. But it rather transitions. So the laminar boundary layer transitions into the turbulent boundary layer. So there is not a very fixed, sharp interface. Okay. So how do you basically distinct them is by using Reynolds number. So Reynolds number for a flat plate REX can be written as rho u infinity x and mu. Sorry. Okay. So at laminar boundary layer region, the inertial and viscous terms balance each other. Inertia. Balance each other. So as because they are the only one acting on each other, and we have assumed that okay, there is no body force term and the flow is steady. So Yeah, assuming steady. So then one can do the order of magnitude analysis because they balance each other out. So one can write in a way that okay, rho okay, so yeah, velocity is in the x direction, and yeah, okay. So so on rearranging, one can write delta square is equal to mu x square by x. Okay. So this expression will give you the boundary layer thickness, but only at the laminar region. Okay. Okay. Now the exact Blassier solution is okay. Now this is the exact solution. Now we have discussed the boundary layer, so now we shall discuss about the displacement layer. Yeah. Now another quantity that is generally associated with the boundary layer thickness is the displacement thickness. It is generally represented by delta star. Okay. Now, how, I mean, the displacement thickness is generally one can kind of come upon it by forming the taking into account of the reduced mass flow rate. So comes into picture when the reduction in mass flow rate is taken into account. Okay. Due to the presence of boundary layer. Okay. So mathematically, one can write the reduction in mass flow as integration of 0 to infinity of rho into u infinity minus u velocity b dy. So yeah, basically we are performing the volume integration. So because the width is constant and yeah, we are now integrating in terms of height and the velocity. So the u is here the function of the height in the y-axis. U is a function of y. So yeah, we are performing the integration, and here the u infinity, the free stream velocity will be constant. So basically, as we are going up in the height, the u will be getting closer to the u infinity, and as we are going lower to it, so the deviation becomes greater. And this deviation we are integrating from 0 to infinity. So basically, if you go towards the infinity, you will then again come across the free stream velocity eventually. So this limit can be now reduced to the delta, the which is actually the boundary layer thickness. So because the U will vary in the boundary layer thickness region only. So after that, it would become free stream velocity U infinity. So one can reduce this limit. So now approximating, we can it can be approximated as rho infinity b delta star let. So now this is what is the displacement thickness. So basically displacement thickness will take into account of that. So let me just draw the diagram. So with boundary layer thickness, you can see that there is a gradient in the velocity. Okay, so yeah. So then one can basically rearrange it to get 0 to infinity dy. So now as okay, so this will give you the displacement thickness. Fine. Now let us just discuss another associated quantity before we go to do the assignment questions. So the another associated quantity with the boundary layer thickness is the momentum thickness. Now, what is momentum thickness? So basically, in the displacement thickness, the displacement thickness came into the picture because we took into account the reduction in the mass flow rate. Now, instead of taking the reduction in the mass flow rate as into account, how about if somebody takes the reduction in the momentum as the parameter, then one can come into the take momentum thickness as the reduction in the momentum flow rate because of the presence of the boundary layer. So yeah. Okay. So one can write several cases. Okay. So can be approximated the momentum flow rate without boundary layer. Okay, so now mass flow rate. So this rho QBL is the mass flow rate, and this is the approximated. So, but one can actually arrive. So this QBL, when you expand it, it is just basically the volume integration of the velocity. So because the velocity will vary in the height, so yeah, you need to perform the integration with respect to height, so 0 to infinity. Now, similarly, now this was the mass flow rate. How about the momentum flow rate? We just substitute. So basically, you got the rho QBL, combine that. So 0 to infinity, 0 to infinity. Just make it okay. So this was the rho QBL, right? So just multiply u infinity in that. U infinity U B D Y. Okay. Now now with boundary layer, what would happen is, because here when you approximate that, okay, there is no boundary layer, so you are taking that, okay, the velocity field has no variation with respect to y-axis. So everything is just like a plug flow with the velocity, average velocity of u infinity. So, but with boundary layer, so there will be a variation, and that u infinity will change into u. So yeah, basically that is the difference. So now with this difference, when you take into account of the reduction in the momentum flow rate due to this difference, so that will give you your momentum thickness. So yeah, subtracting them to take the reduction into account. E. Now this can be approximated that okay, let us assume this reduction in an ideal this reduction can be expressed in terms of the free stream velocity as u infinity square and b, and let the thickness be. So basically when you are integrating, so yeah, this would become theta. Let so this implies so the momentum thickness 0 to infinity u by u infinity 1 minus u by u infinity dy. So now we can change the upper limit just like we have done as we have done in the previous so with the displacement thickness. So this will also be similar to that. So basically till the boundary layer thickness. So yeah, this will give you your momentum thickness. Okay. So now with this knowledge we can do the assignment questions. So the question number one, if you could go back and see, is which of the following is the main property that affects a boundary layer? So the options are temperature, pressure, viscosity, and surface tension. Surface tension, no doubt, it will not affect. Temperature, it will not affect. So temperature, in a way, can affect because viscosity sometimes in a real world, viscosity will change with temperature and pressure. But yeah, but on an ideal case scenario, we can ignore the influence of the temperature and pressure, and it will just be the viscosity that will affect the boundary layer. So that will be the main property. So even the temperature and pressure will come into play through the viscosity because they affect the viscosity and then the viscosity will further affect the boundary layer thickness. So yeah, so viscosity is the one. Okay, so the second question. So there is a common data associated with the question number 2, 3, 4, and 5. So the question goes as the velocity profile in the laminar boundary layer over a flat plate can be approximated as u by u infinity is equal to y by delta, where x and y are the coordinate along and normal to the flat plate respectively. U infinity is the free stream velocity, delta is the boundary layer thickness or the disturbance thickness. The free stream velocity u infinity is 1 meter per second. Assume that the boundary layer transition occurs at Reynolds number value of 5 into 10 to the power 5, and the kinematic viscosity of the fluid is 1.5 into 10 to the power minus 5 meters square per second. So everything is in SI units. Okay. So the question number 2 then says that okay, if delta x and delta by x is 3.46 by square root of Reynolds number, then calculate the distance, the transition length in meter from the leading edge of the plate up to which the flow in the boundary layer is laminar. Provide your answer to the one decimal place. Okay, so basically for the question number 2, we need to get the Reynolds number value. Because Reynolds number value will contain your rho b d by mu or rho u infinity by transition length by viscosity, dynamic viscosity. So yeah. So Rex is equal to rho u infinity into L transition by mu. Or one can write that basically u infinity L trans by kinematic viscosity. So because we have been given the kinematic viscosity value. So and the transition occurs at so yeah given Rex is equal to 5 into 10 to the power 5 and kinematic viscosity as 10 to the power minus 5 meter square per second. Okay. Oh, sorry, 1.5. 5 into 10 to the power minus 5 meter square per second. That, or the Reynolds number, transition Reynolds number is 110 to the power 5, and the 10 meter viscosity is given this. And the U infinity is 1 meter per second. 1 meter per second. So everything is in SI unit. So this implies that the transition length is basically 5 into 10 to the power 5 into 1.5 into 10 to the power minus 5 by 1. Cut it. So 5 into 1.5 would basically become 7.5, 7.5, because yeah, meter. So yeah, the answer is okay, 7.5 meters. On the question number 3, calculate the boundary layer thickness in centimeters at the x is equal to transition length. Provide your answer with the 2 decimal place. So now, as they have also provided with the delta by x is equal to 3.46 by square root of a Reynolds number. So we just need to do that. So yeah, given delta by x is equal to 3.46 by square root of Reynolds number x. Okay, so and where, so basically this x is L transition. So L transition is equal to 7.5 meter, and Reynolds number x is, so this is to be calculated at the L trans, right? And in the L trans, the Reynolds number was given to be as basically 5 into 10 to the power 5. 5 into 10 to the power 5. Okay. So this implies that delta is equal to 3.46 into 7.5 into 10 to the power 5. Okay. So this would mean 0.0367 meter or 3.67 centimeters. Okay. So the fourth question state, calculate the displacement thickness in centimeter at transition length. So okay, so previously we calculated just the boundary layer thickness. Now we are supposed to calculate the displacement thickness. Okay, so now the displacement thickness is given as delta star is equal to integration 0 till boundary layer delta 1 minus u by u infinity, and the integration is performed with respect to y. So given in the question was that okay, u by u infinity can be approximated as y by delta. So this becomes 0 to delta 1 minus y by delta integrated with respect to y. So this would become So this would basically become delta by 2 is equal to 1.835 centimeters. Okay. Now the question number 5 says calculate the momentum thickness in the centimeter at x is equal to transition length. Provide your answer up to the two decimal cases. Okay, so now we need to calculate the momentum thickness. Now, if you could recall that what was the momentum thickness? The momentum thickness was also 0 to till delta u by u infinity 1 minus u by u infinity dy. So So as it has been given that okay, it can be approximated as y by delta, u by infinity can be approximated as y by delta. So this would become okay. Now performing the integration. Y square by 2 delta minus y cube by 3 delta 0 till delta. So if you do it, it would come out to be delta by 6 is equal to 0.61167 centimeters. Okay. So yeah, it is in the same range. So these two are actually not necessarily same. Okay, so now let us discuss the rest of the remaining assignment questions. Question number 6, 7, and 8. They have a common data. According to the Placier solution, the boundary layer thickness delta and the screen friction coefficient CF over a flat plate is given as follows. Delta by x is equal to 5 by square root of Reynolds number, and the screen friction coefficient is given as 0.664 divided by the square root of Reynolds number. Consider the flow of water over a flat plate. So the fluid, the water's density is given as 1000 kg per meter cube, and the viscosity is 0.001 Pascal second. And the length of the flat plate is 0.1 meter, and the free stream velocity or the bulk velocity is given as 1 meter per second. So the water is introduced to the flat plate at 1 meter per second. The boundary transition occurs at Reynolds number value of 500 to the power 5. Now, the question number 6 says, what is the Reynolds number at the plate end? So we need to calculate the Reynolds number value at the plate length of 0.1 meter. So yeah, okay. So given viscosity 0.001 Pascal second, rho is 1000 kg per meter cube, and L is 0.1 meter, and U infinity is 1 meter per second. Let me just check everything is right. So length is this. Okay, fine, everything is fine. So into 0.1 by 10 to the power minus 3 is equal to 10 to the power 5. Okay. This is the Reynolds number value at the plate end. Now let us discuss the seventh question. Yeah. Our seventh question says calculate boundary layer thickness at the plate end delta at x is equal to L, provide your answer. So yeah, we calculated the Reynolds number. Now we just need to substitute it in the boundary layer thickness equation. So yeah. is okay. So given so okay. Now the last question, eighth question says find the drag force on the plate if the plate width is 1 meter. Provide your answer in Newton. Okay. Now to find the drag, so basically no, the drag force Ft is given as the drag coefficient multiplied with the projected area into the rho u infinity square by 2. So we need to first, so basically we have been given the u infinity, we have been given with the density, and we have been given with the area. So only thing we need to get is the friction coefficient, skin friction coefficient. So the Cf is equal to given Cf is equal to 0.664. 0.664 divided by under root of Reynolds number x. Okay. Six four divided by Reynolds number. So the Reynolds number is here is 10 to the power 5. Okay. So that would basically mean 0.1021. Okay. Our given plate width is 1, and so basically the area and the length of the plate is given as 0.1 meter. Density is 1000, u infinity 1 square divided by 2. So basically 1000 so 1002.1 0.21 is equal to, so this is the solution of question number 8. So generally, the what is drag? The drag is the force exerted by the flowing fluid on a body in a flow direction. Okay, and the drag happens by the normal, by the contribution from the skin friction force, basically the friction force and the pressure force, force on the pressure term. So the pressure term will exert a normal force to the surface, and whereas the viscous term will exert a shear force. So and yeah, so basically the overall drag is the contribution from the form drag and the skin friction drag. And so basically, and the components of the force that are normal to the flow direction would be called as lift. Instead, I could have shown you the integration. Okay, no problem. So when a flat plate is placed parallel to the flow, so here the drag will only be a contribution. So because we are not taking any body forces and the pressure because it is a flat plate, so it will act, but we are because it might also happen from the other side also we are, so that's why there will be a net pressure contribution, net zero pressure contribution. So here the drag force, here the drag force skin friction only. So here it is skin friction only. And generally the skin friction is given by CF is equal to 0.664 or basically whatever constant, but in the question it has been given to us as 664. So this is called as skin friction coefficient. Skin friction coefficient. Okay. So and then one can write that okay, the drag force is equal to 0 to L because you know this rho u infinity square by CFB dx. Okay. So this would become 2 rho u infinity by CF. So the CF, if you expand, it is the Reynolds number, right? So you will have a contribution of x in here. So basically what would become as B mu rho u infinity 0 to L dx by delta x. So if the Reynolds number is constant, then it would just become half rho u square CF into area. which I have taken here. So because the Reynolds number is not varying, or I can just write that also. Okay. So if Reynolds number is not constant, then Ft is equal to U infinity B mu rho U infinity 0 to L dx by square root of x. Okay. So when you integrate it, so basically this would become 0.664 rho U infinity square B mu L by rho U infinity. Okay. Now as now one can write this in terms of drag coefficient. So as drag coefficient is equal to drag force divided by half rho U infinity square by area. So basically this would make it 2 into 0.664 into mu rho U infinity L. So this is basically your Reynolds number. So this implies that the drag coefficient would be okay. Okay, so let's do some problems from the Fox and McDonald's book. Uh, the roof of a minivan is approximated as a horizontal flat plate. What is the length of the laminar boundary layer as the function of minivan speed? V as the minivan accelerates from 10 meters per hour to 90 meters per hour. So yeah, length of the laminar boundary layer. So Transition from laminar boundary layer occurs at node number 5 into 10 to the power 5. Okay, so we have the node number, we have the critical node number, we have the U infinity, and just so if we take consider air as the fluid medium, then the density 1 kg per meter cube and viscosity. Okay. So aerodynamic viscosity would be Pascal second. 18.13. Instead of 1, if we take 1.2 kg per meter cube. Okay. So if this is our fluid medium, consider air as the fluid medium at 25 degrees Celsius. So yeah. -18.13 -6 rho VD. And so basically at 10 meters per hour. So basically, okay, for now let us just do infinity. Okay, so at 10 meters per hour, what it would become is 10 meters per hour. Okay, 10 divided by 60. Okay, so this would be 0.00278 meters per second. Okay, so L laminar would become sorry, let me just calculate that. 18.1316 is equal to, okay, divided by 1.29 is equal to 7.027 u infinity is equal to 7.027 into u infinity will be 0.00278 0.0195 meter. Okay, and at u infinity 90 mph, so it accelerates, so basically changes its velocity from 10 meter per hour to 90 meter per hour. Okay, okay, it is not per hour. Okay, also meters per it's miles. Okay, okay, instead of miles, let me just write it as kilometer per hour. Okay, kmph. So that would basically mean 3 2.78 kmp. Sorry, this will be meter per second, right? Meter per second. Okay. 7.027 into 2.79. Okay, okay. So, okay. Similarly, it would also jump. And let this also be kmph. So if it is 90 kmph, so basically it is 3 meters per by 3600 seconds. Okay. Seven point zero two seven into 25. This would basically mean 175.675 meters. Okay. That's a huge difference. 19.6 into, yeah, so let us go to the second question. Say this question is also very similar to the first one. Here also we just need. So 1 meter into 2 meter sheet of plywood is attached to the roof of your vehicle after being purchased at the hardware store. At what speed will the boundary layer first start becoming turbulent? At what speed is about 90% of the boundary layer turbulent? So, maybe just we can keep that. Okay. Okay. So here also we will do the same Renault number. Using the same Renault number, we will get the uh, yeah, we will get the velocity. Okay. Okay. So let the now again the 20 centigrade air if we take, so we would basically the density is equal to 1.29 kg per meter cube, and the viscosity is 18.13 Pascal second. So now we just need to calculate the U infinity. So this implies that U infinity is equal to, so the kinematic viscosity can be then calculated, right? Okay. 0.13 divided by 0.29. Okay, it's fine. Okay, so this would become 18.13 into 5. 9.065 divided by 0.065 divided by 29 into 2. Okay, so 3.51. Meter per second. So at this velocity, it would become. So at this velocity, the boundary layer will start becoming turbulent. Now it further asks at what speed is about the 90% of the boundary layer turbulent. So when 90% of the boundary layer is turbulent, that means that the L we now have is 2 into 0.1 is equal to basically 0.2. So that basically means that okay, zero point 0.2, right? So 35.14 meter per second. Another very similar problem, but instead of flat plate, we are taking flow around a sphere, a boundary layer. For flow around a sphere, the boundary layer becomes turbulent around Reynolds number. So notice here instead of x we have taken as d. So basically the diameter that represents the sphere diameter. So the Reynolds number is equal to 2.5 into 10 to the power 5. Find the speeds at which an American golf ball of diameter 1.68 inch and a British golf ball of diameter 41.1 millimeters. So yeah, notice the imperial and the SI unit. So yeah, and a soccer ball of 8.75 inches. Develop turbulent boundary layers and so okay, at which the turbulent boundary layers gets developed. Assume standard atmospheric condition. Okay, so here the critical Reynolds number given to us is 5 into 10 to the power 5. This is the critical Reynolds number. And take the okay. So we have rho, we have mu, we have Reynolds number. Now the only thing we need is the velocity and yeah, the diameters. So we have been given the diameters, so rho v by mu. So yeah, so 1.68 is 0.042 Okay. So U infinity is equal to 2.5 into 10 to the power 5 into 18.13 into 10 to the power minus 6 by 1.29. 0.0427. So this would basically give me, let me just do the calculations. Okay. No, similarly. Basically, it will become 2.5 into 18.3 is equal to divided by 0.29 into 0.0411 equal to this 85.488 meter per second. Okay, and then C for soccer ball of diameter 8.75 inch, which is basically 0.222. Okay, so this will become 2.5 into 18.13 is equal to divided by 1.29 into 0.222. Okay, so 15.827 meter per second. Okay, so as the diameter, so basically diameter increased, the velocity decreased to compensate basically so that the Reynolds number stays consistent. Okay, so yeah. Now the next question is an approximation for the velocity profile in a laminar boundary layer is given below. Does this expression satisfy boundary conditions applicable to the laminar boundary layer velocity profile? Evaluate the delta star by delta, basically displacement thickness by boundary layer thickness and the momentum thickness by boundary layer thickness. Okay. So we need to first check the boundary conditions that, okay, is it able to satisfy the no slip boundary condition and that at delta, basically at delta, whether the u is equal to the free slip and the bulk velocity or not, capital U or not. So if it's satisfied, it satisfies. Or basically that, okay, there is zero gradient at the delta. At y is equal to delta, there should be zero gradient. So the boundary conditions. So the boundary conditions are no slip and the free slip boundary conditions. So the no slip boundary condition states that the velocity should be zero at y is equal to zero, and the free slip boundary condition states that okay, y is equal to delta, the velocity should there should be no gradient in the velocity. Okay. Okay. At y is equal to zero, this term, entire RHS will go into zero. So basically, this goes to zero. This goes to zero. Plus this goes to zero. Okay. So u is equal to zero. Satisfies no slip boundary condition. Now at y is equal to delta, 2, so this will become delta by delta minus 2 delta by delta. So this will also become 1 plus delta by delta 4. So this implies u is equal to u. Okay. Now du by dy is equal to 2 by delta minus 2 delta cube. So this will become 6y square. This will become delta to the power 4. 4 basically this would become 2 by delta minus 6 by delta plus 4 by delta. So this would become 0. So yeah, it also satisfies free bound condition. Okay. Now for displacement thickness, it can be written as 0 to infinity 1 minus u by u infinity into with respect to dy. Okay, so delta star by delta is equal to so the differentials can be changed to this so that a limit goes from 0 to 1. Okay, and let this okay. So so the u by u infinity can be rewritten in terms of nabla. This y by delta is 2 nabla minus 2 nabla cube plus nabla to the power 4 or nabla or eta, whatever you want to say. So then what happens is delta star by delta becomes So this would become the delta star by delta as 0.3. Now, now for momentum thickness, what we can do 0 to infinity. So similarly, here also we can do that same change. Okay. Now you are 9. Okay. 0 to 1. Okay. So now a tennis ball has with a mass of 57 gram and diameter of 64 millimeter is dropped in a standard sea level air. Calculate the terminal velocity of the ball. So at the standard sea level, so we have STP. So standard temperature and pressure, the viscosity of the air or the kinematic viscosity. So given kinematic viscosity is 1.45 into 10 to the power minus 5 meters square per second. Okay, and we have the density of air as 1.23 kg per meter cube. Air. Okay, and the mass of the tennis ball is 57 gram or 0.057 kg. Okay, and diameter is 64 mm, 0.064 meters. Okay, then area is equal to pi d squared by 4. Just basically, let me just do the calculation. Point 0.064 divided by 4. Okay, 0.00322. Okay, meter square. So now we assume the flow to be at higher Reynolds number. So the drag coefficient can be approximated as 0.5. Okay. At terminal velocity. So basically, terminal velocity. The drag force balances the weight. So basically, if we can write a drag force is equal to mass into acceleration, or basically mass into small g 9.8. Now this drag force is also given as okay. So this terminal velocity ut. So if we substitute each and everything under root of 0.057 into 9.81 into 2, density is 1.23, area is 0.00322, and drag coefficient is 0.5. So yeah, and that the velocity becomes. So yeah, let me just do the calculations. 0.057 into into divided by 1.23 into 0. Find that also 0.3 to 0.5 is equal to answer 23.8 and 23.764 meters per second. Okay. So yeah, that will be all for this week. Okay, see you the next week. Thank you.